This lecture is going to cover logistic regression, which is one of my all-time favorite topics in statistics, as well as a number of other smaller topics that are associated with logistic regression. Now consider this scenario. We want to use a student's GRE score to predict if that student will be admitted into graduate school. Now taking a look at the data over on the right, we have whether or not the student was admitted in column C1, and we have their corresponding GRE score in column C2. Now the problem with the data in its current form is the fact that our response variable is categorical. What we need to do is create a dummy variable. So let's code the student being admitted into graduate school as 1, and we'll code the student not being admitted as 0. What this allows us to do is now have two quantitative variables that we're comparing. So one possible strategy that we could implement is to use regression to predict the probability that a student will be admitted into graduate school. We may not be able to get a definitive yes-no prediction, but we can at least assign a probability that they'll get into grad school. So we go ahead and create a scatter plot of the admission indicator variable 1, 0 versus the student's GRE score. Notice that whenever we fit a simple linear regression line to the data, we end up with a big problem using simple linear regression to predict a student's admission probability. Linear regression is unbounded. And so what this means is that at some point in any logistic regression, you're going to get predicted probabilities that don't make sense. In this case, your linear regression model is going to predict a negative probability for GRE scores below 420. And it's going to give you a probability above 1 for GRE scores above 790. The takeaway here is that we need some kind of a transformation on this regression model that's going to restrict our predictions so that they stay between 0 and 1, which are the appropriate bounds for probabilities. That brings us to logistic regression. Logistic regression is a statistical model that's used to predict the probability that some outcome from a categorical response that has two categories will occur, given the values of the predictor variables. The logistic regression equation looks like this. Over on the left-hand side, we have the probability that y is equal to 1. This is representing the probability that we witness a success. This probability is calculated using the equation that you see over on the right. Now notice we actually have the multiple regression equation in this model, only it appears up in the exponent. We have e to the beta naught hat plus beta 1 hat times x1 plus beta 2 hat times x2, all the way out through beta k hat times xk. We then divide that by 1 plus the exact same thing we had up in the numerator, e to the regression model. Now, this transformation that you see here that uses the exponential function is called the logit transformation. And this logit transformation is what restricts the probabilities to being between 0 and 1. The other thing that I want to point out here is the fact that these regression coefficients are not able to be calculated by hand. Every single statistical software out there uses iterative methods in order to find the best set of regression coefficients. Let's go back to our graduate school example. Again, we're using GRE score to predict if a student will be admitted into graduate school. So if we take the 20 observations that we have in Minitab and run a logistic regression on them, this is the output that we get for the coefficients. We have a row for the constant and a row for our predictor, GRE score. Setting up the logistic regression model and the logistic regression equation has a couple of differences just like we saw back in linear regression. The logistic regression model has e of y, the expected value of y, on the left-hand side. On the right-hand side, just like we did in linear regression, we're only plugging in the values of the parameters. We have e to the beta naught plus beta 1 times x divided by 1 plus e to the beta naught plus beta 1 times x. Because these are parameters, they don't actually have any values associated with them. Note also that we don't put the plus e in the logistic regression model like we did in linear regression. The logistic regression equation has, again, that probability that y is equal to 1 over on the left-hand side. And now we're able to replace beta naught hat and beta 1 hat with the values that we got from the Minitab output. We have e to the negative 9.09 plus 0.0149 times x, where x represents the student's GRE score, divided by 1 plus the same thing that we have up in the numerator, e to the negative 9.09 plus 0.0149 times x. Now, if we take the logistic regression equation from the previous slide and plot it on a scatter plot, this is what we end up with. A logistic regression equation is always going to give us an S-shaped curve. What this means is, as GRE score increases, the predicted probability of being admitted into graduate school is also increasing. However, notice that the rate of change of the probability is not constant like it would have been in simple linear regression. We notice a very steep increase in the predicted probability around x bar, right around a GRE score of 600. But notice that the increases in the predicted probability is much more gradual for extreme x values. What this curve is telling us is the predicted probability of being admitted into graduate school approaches 0, gets very close to 0 for small GRE scores, and it gets very close to 1 for the most extreme large GRE scores. I also want to point out here that in this logistic regression, we had a positive slope. If we run a logistic regression and we see a negative slope, then the opposite is going to hold. The curve is going to approach 1 for small values of the predictor, and we're going to have predicted probabilities close to 0 for larger values of the predictor. Let's suppose that now we want to make a prediction, and we want to find the predicted probability that a student who scored 650 on the GRE will get admitted to graduate school. Now, just like we did back in simple linear regression and multiple regression, this is just a matter of plugging in 650 into the logistic regression equation. So the probability of a success, or being admitted into graduate school, is going to be e to the negative 9.09 plus 0.0149 times the GRE score of 650, divided by 1 plus the exact same thing that we have up in the numerator. Working out the exponent is going to give us 0.595, so that whenever we take e to the 0.595, we get 1.813. In the denominator, we're going to get 1 plus that, or 2.813. 1.813 over 2.813 gives us a predicted probability of 0.6445. Now, what we can do is take this probability and make a prediction. Because this predicted probability is greater than 0.5, we would predict that this student is going to be admitted into graduate school. So the way you can think about this is that there are two parts to logistic regression. One gives you an exact predicted probability. The other is the prediction that you make. Is it going to be a success or is it going to be a failure? 0.5 is typically the cutoff that we use in order to separate the successes from the failures. Another thing that we can do with the logistic regression equation is find the cutoff between a success and a failure. In other words, what value of x, or what GRE score, would be the cutoff between being predicted to be admitted and being predicted to be rejected. What we need here is a predicted probability equal to 0.5, and this is going to occur whenever the numerator is equal to 1. Because we add 1 to the denominator, if the numerator is equal to 1, then the denominator is going to be equal to 2, meaning that whenever the numerator equals 1, we have a predicted probability of 0.5. In order to get the numerator equal to 1, what's up in the exponent, the negative 9.09 plus 0.0149 times x, is going to have to be equal to 0, because e to the 0 is equal to 1. So solving this equation is going to give us 9.09 divided by 0.0149, giving us a GRE score of 610. So as a result, students who score under 610 are going to be predicted to be rejected from graduate school. Students who score above 610 will be predicted to be admitted. Another way of thinking about this is if we plug in any GRE score above 610 into our logistic regression equation, we're going to get a predicted probability above 0.5, and if we plug in any GRE score below 610 into our logistic regression equation, we're going to get a predicted probability less than 0.5. Two other metrics that we can use to describe the likelihood of events occurring are the odds and the odds ratio. The odds are defined to be the probability that some event will occur divided by the probability that that event will not occur. Two ways of calculating this out that are identical are taking the probability of A and dividing by the probability of its complement, which is equivalent to the probability of A divided by 1 minus the probability of A. The odds ratio is exactly what it sounds like. It's a ratio of odds. The odds ratio is comparing how likely event A is to occur compared to some other event B. Odds ratio is denoted by OR, and it's equal to the odds of event A divided by the odds of event B, which again can just be calculated by taking the probability that A will occur divided by the probability of its complement. That ratio divided by the odds for event B, the probability that event B will occur, divided by 1 minus the probability that event B will occur. So let's first consider the odds for our student who has a GRE score of 650. We want the odds that this student will get into graduate school. Now, we already calculated out that the probability that this student gets admitted into graduate school is 0.6445. The odds of admission are going to be the probability of admission, 0.6445, divided by the probability of being rejected, 1 minus 0.6445. That ratio gives us 1.813. What this number means in context is that the probability of being admitted into graduate school is 1.813 times the probability of being rejected for a student who has a GRE score of 650. So the student who scores 650 on the GRE is almost twice as likely to be admitted compared to being rejected. For an odds ratio, we need two different events. Here, we're going to calculate the odds ratio for a student with a GRE score of 650 compared to a student who has a GRE score of 600. Again, we already know that the student who scored 650 has a probability of getting into graduate school of 0.6445. If we were to repeat that calculation for the student who scored 600, we would find that their predicted probability of admission is 0.4626. Setting up the odds ratio, we'll have the odds for the student who scored 650 up in the numerator, and the odds for the student who scored 600 in the denominator. So we have 0.6445 divided by its complement, 1 minus 0.6445. The odds for the student who scored 600 are going to be 0.4626 divided by 1 minus 0.4626. This will give us a ratio of 1.813 divided by 0.861. So our final odds ratio comparing the students who scored 650 and 600 is 2.106. What this number means in context is the student who scored 650 on the GRE is 2.106 times more likely to be admitted to graduate school compared to the student who scored 600 on the GRE. Now let's discuss how we can test the logistic regression model. Just like in multiple regression, there are two different types of tests that we can do. We can test the full model, or we can test individual predictors. To test the full logistic regression model, the null hypothesis is going to be that all of our betas are simultaneously equal to 0, and the alternative is going to be that at least one of our betas is not equal to 0. The test statistic is denoted by x squared. It follows a chi-squared distribution with k degrees of freedom, where k denotes the number of predictors in the model. This test statistic is called the Wald statistic. However, because these coefficients in logistic regression are calculated iteratively, The test stat is most easily obtained using software. It can be calculated out by hand, but you need some more advanced metrics that go beyond the scope of this class. Once we've tested the full model, we can then go and look at each of the individual predictors. The null hypothesis for each predictor would be that beta I is equal to 0 against the alternative that beta I is not equal to 0. And then your test statistic is going to be the estimated parameter, beta I hat, divided by its corresponding standard error. And this is actually going to give you a standard normal test statistic. So let's see how testing the logistic regression model works. We want to use age, family income in thousands of dollars, and gender to predict marijuana usage in the past month for a random sample of 719 college students. Right now, we want to know if the overall model is significant in predicting marijuana use. So our logistic regression model is going to be e to the beta naught plus beta 1 times x1, where x1 is age, plus beta 2 times x2, where x2 is income, plus beta 3 times z, where z is a dummy variable for gender, with males being coded as 1 and females being coded as 0. We'll take that and divide it by 1 plus e to the linear model. The null hypothesis here is that all three of our betas, beta 1, beta 2, and beta 3, are simultaneously equal to 0. The alternative is that at least one of the betas is not equal to 0. Now, when you run a logistic regression in Minitab, this is one of the other outputs that you'll get. We've already taken a look at the coefficient output. The output that you see here can be used to assess the significance of the full model. The top line where you see regression is going to contain the information that we need in order to run this full test. So our test statistic is going to follow a chi-squared distribution, and our test stat is going to be equal to 20.93 with 3 degrees of freedom. The critical value, giving us 5% of the area in the upper tail of the chi-squared distribution with 3 degrees of freedom, is 7.815. We can also use the p-value from this output. The area up above 20.93 in a chi-squared distribution with 3 degrees of freedom is 0.0001. What this tells us is that we can reject the null hypothesis and conclude that the full model is significant in predicting marijuana usage over the past month for college students. Now that we know the full model is significant, we can go ahead and test the individual predictors. The process for testing the individual predictors in logistic regression is no different from what we did back in multiple regression. For testing age, we'll set up the null hypothesis beta 1 equal to 0 against the alternative beta 1 not equal to 0. For income, we'll test beta 2 equal to 0 against beta 2 not equal to 0. And for gender, we'll test beta 3 equal to 0 against beta 3 not equal to 0. In order to calculate out the test statistic, we're going to use the coefficient output over on the left. We'll take the estimated regression parameter, 0.2477, and divide by its standard error, 0.0749, giving us a test stat of 3.31. This test statistic follows a standard normal distribution. Now, one of the properties of the standard normal distribution is if you square a standard normal random variable, you end up with a chi-square random variable with a single degree of freedom. So if we square this 3.31, we're actually going to end up with the 10.9389 that you see in the chi-square column in the output over on the right for the row for age. This means that we can use that corresponding p-value of 0.0009 as the p-value for testing to see if age is significant. What this means is that we reject the null and conclude that age is significant in this model. Then we can do the same thing for income. We take the estimated slope for income, negative 0.00728, divide by its standard error of 0.0061, giving us a test statistic of 1.19. Squaring that value would give us the 1.4208 that you see over on the right, which corresponds to a p-value of 0.2333. This tells us that we would fail to reject the null and conclude that income is not significant in predicting marijuana use. And finally, for gender, we take the estimated slope of 0.526, divide by its standard error of 0.179. That gives us a test statistic of 2.94. Squaring the 2.94 would give us the chi-squared statistic that you see over on the right of 8.6662. This would correspond to a p-value of 0.0032, meaning that for gender, we would reject the null and conclude that it is significant in predicting marijuana use. So in the end, here are the conclusions that we can come to. We know that age is significant, and because the coefficient was positive, we're able to deduce that older students were significantly more likely to have used marijuana within the last month compared to younger students. Income was not significant in predicting marijuana usage over the past month. This is an indication that students of all different incomes were about equally likely to have used marijuana. And finally, with gender, gender was significant, and because the coefficient was positive, we can conclude that males were significantly more likely to have used marijuana in the last month compared to females, because the males were coded as 1 in our dummy variable, and females were coded as 0 because they were acting as the baseline category. Let's talk about what these regression coefficients mean in context, because they're a little bit different from multiple regression. In multiple regression, we said that a regression coefficient was equal to the expected or the predicted increase in the response given a 1-unit increase in the value of the predictor. The problem is that in logistic regression, beta I hat by itself does not have a nice interpretation. Our solution to this, though, is to exponentiate the regression coefficient. Now, the interpretation is a little bit different depending upon if you have a continuous variable or if you have a dummy variable. If your variable xi is continuous, then e to the beta I hat represents how many more times likely a success is whenever the value of the predictor is equal to x compared to whenever it's equal to x minus 1. On the other hand, if x sub I is a dummy variable using reference cell coding, that is, each of your categories is coded as either 0 or 1, then e to the beta I hat represents how many more times likely a success is for level x sub I, the category coded as 1, compared to the baseline category, the category that's coded as 0. We can also calculate out confidence intervals for these parameters. A confidence interval for the slope would be given by beta I hat plus and minus some critical value from the standard normal distribution times the standard error of the estimate of the parameter. However, again, we're going to run into this issue where these confidence intervals don't have a nice interpretation either, just like the individual regression parameter. Instead, what's more frequently used in logistic regression is a confidence interval for the odds ratio. What we can do is we can still calculate the confidence interval for the slope that you see up above, but instead we're able to then exponentiate the endpoints and end up with a confidence interval that does have a nice interpretation. Let's take a closer look at these regression coefficients and see what more they can tell us, starting with age. The estimated slope on age was 0.2477. Now again, this 0.2477 by itself doesn't tell us much. However, exponentiating 0.2477 is going to give us our odds ratio of 1.281. Because age is a continuous predictor, what this tells us in context is that a college student of a particular age is 1.281 times more likely to have used marijuana within the past month compared to a student who is 1 year younger. Another way of thinking about this, as a more concrete example, is that a student who is 21 years old is 1.281 times more likely to have used marijuana compared to a student who is 20 years old. The next thing that we can do is calculate out a 95% confidence interval for the parameter estimate. We center the interval at 0.2477, add and subtract the critical value for 95% confidence from the standard normal distribution, 1.96, and then multiply that by the standard error of the estimate, 0.0749, which gives us a final confidence interval of 0.1009 up to 0.3945. Again, this confidence interval doesn't mean much in context other than it doesn't contain 0, so age is significant. Exponentiating these endpoints gives us a confidence interval for the odds ratio. E to the 0.1009 gives us 1.106, and e to the 0.3945 gives us 1.484. So what this is telling us is while 1.281 is the best estimate that we have of the odds ratio for age, plausible values for this odds ratio range anywhere from 1.106 up to 1.484. Now let's see what gender tells us about marijuana usage. The estimated parameter for gender was 0.526, so exponentiating this coefficient gives us 1.692. What this means in context is that males are 1.692 times more likely to have used marijuana in the past month compared to females. Again, the way that we were able to come to this conclusion is because males were coded as 1 in our dummy variable and the females were coded as 0. We can again calculate out a 95% confidence interval for the regression coefficient, 0.526 plus and minus 1.96 times the standard error of 0.179. That's going to give us a lower bound of 0.175 and an upper bound of 0.877. And to find a 95% confidence interval for the odds ratio, we exponentiate each of these endpoints. E to the 0.175 gives us 1.191, and e to the 0.877 gives us 2.404. So let's talk a little bit about the confidence interval for this odds ratio. What we can say for the interpretation is that we are 95% confident that males are between 1.191 and 2.404 times more likely to have used marijuana within the past month compared to the females. Now we can also use this confidence interval for the odds ratio to determine that gender is significant. Just like in a confidence interval for the regression parameter, where we look for 0 in the interval, for an odds ratio confidence interval, we actually look for 1. Because this confidence interval for the odds ratio does not contain 1, that's an indication that the predictor, gender, was significant. After running your logistic regression model, what you can do is obtain the predicted probability for each observation, and then use these predicted probabilities to determine the accuracy of your model. There are two common ways of classifying observations, one of which we've already seen. The first method is to use 0.5 as the cutoff for classifying an observation as either a success or a failure. The other method involves looking at the distribution of your response variable. If you notice that either the success outcome or the failure outcome occurs much more frequently than the other, what you can do instead is choose a different logical probability as the cutoff for your success or failure. And the most common thing to do is to choose a cutoff that's very close to the proportion of successes that's in your sample. One way that we can organize the results and describe the performance of a logistic regression model is through a confusion matrix. What we first do is classify each observation as a success or failure based on the predicted probability. The confusion matrix, which is the 2x2 table you see down in the bottom right, compares the actual response against the predicted category. Now, to fill in the confusion matrix, we count the number of correctly classified successes and failures, along with the number of incorrectly classified successes and failures. In this table, A represents the number of true positives, or the number of observations that were both predicted to be successes and actually were successes. D represents the number of true negatives, which is the number of observations that were predicted to be failures and actually were failures. B represents the false positives. In this case, the model predicted that the observation would be a failure, but it was actually a success. And C represents the number of false positives, which is the opposite of B. This is the number of observations that were predicted to be successes, but were actually failures. In the end, we can calculate the accuracy of the model by taking the total number of correctly classified observations, which is A plus D, and dividing by the total number of observations altogether, which is N. So to finish things off, let's take a look at the confusion matrix for our marijuana example. In the sample, 23.5% of students had used marijuana within the past month, so what we can do is use 25% or 0.25 as the cutoff for classifying the observation. We'll say that any predicted probability less than 0.25 will be classified as a yes, or the student has used marijuana. Any predicted probability above 0.25 will be classified as a no, or predicting that they have not used marijuana. Now, one of the things that the confusion matrix reveals is our accuracy. What you should notice here is that 51 students in this sample were predicted to have used marijuana and actually did. 452 were predicted not to have used marijuana and actually did not. Dividing this sum by 719 gives us our accuracy of 0.6995. A couple of other points. The model actually predicted that fewer students would use marijuana than actually did. The model predicted that 149 of these students would use marijuana whenever 169 of them actually did. And whenever we take a look at where the model missed, whenever the model predicted incorrectly, it was slightly more likely to predict that a student did not use marijuana when they had. This happened 118 times, compared to the opposite, which is whenever the model predicts that the student would use marijuana whenever they actually did not. This accounted for 98 of our incorrectly classified observations.